In this video, we are going to talk about the reactions of alkynes. Let us consider the molecules below. In alkynes, the molecules on the left are called the terminal alkynes, and then the molecules on the right are internal alkynes. What is the difference between terminal alkynes and then internal alkynes? A terminal alkynes is it always have at least one proton that is bonded to one of the carbons bearing the triple bond. But internal alkynes does not have one of the carbons bearing the triple bond bonded to a proton. So this is the major difference between internal alkynes and then terminal alkynes. But we can distinguish between internal alkynes and terminal alkynes by using the Alkynes reagent. Let's consider these two molecules. You see that this is a terminal alkyne, and then this one is an internal alkyne. So let's consider these two molecules. This molecule is a terminal alkyne because we have one of the carbon triple bonds bonded to a proton. And then this one is an internal alkyne because the carbon bearing the triple bond does not have a proton. How will we differentiate between a terminal alkyne and an internal alkyne? So to distinguish between these two alkynes, you put in Alkynes reagent, which is the silver ammonium ion. If you put in the silver ammonium ion, for the terminal alkynes, this proton is highly acidic. And because it is acidic, it can easily lose this proton to the Alkynes reagent, and it will form this carbon ion. And when you lose a proton, the Alkynes reagent will pick that proton whilst releasing silver ions in solution. So it is this silver ion that is going to form a mirror in the test tube, confirming the presence of a terminal alkyne. But for the internal alkyne, there will be no such reaction. So this is a simple test to distinguish between a terminal alkyne and then an internal alkyne. Let's consider these two reactions. If you have a terminal alkyne and you put in a strong base, it appears that you are going to form a carbon ion. So in this case, you are going to form this carbon ion. The terminal alkyne can easily lose this proton because this proton is highly acidic to give you this carbon ion and then ammonia in this case. But in this case of the Grignard reagent 2, this is also a very strong base. So the terminal alkyne will easily lose this proton to give CH3, C triple bond, and this carbon ion, and therefore releasing this in solution, CH4. Now, the driving force behind this reaction is because this proton is highly acidic. Why is the proton on a terminal alkyne highly acidic? The reason is because of S character. In alkynes, the S character is 50%. And then in alkenes, so this carbon triple bond. And then in alkenes, carbon double bond, the S character is 33.3%. And in alkenes, the S character is 25%. So here is 50% for alkynes. Then in alkenes, it is 33.3%. And then in alkenes, it is 25%. For the case of the alkynes, the s orbital is very close to the nucleus, and therefore the electrons are pulled closer to the nucleus than the proton. So this makes the alkyne a little polar. So it has partial positive. So there's a partial negative charge and a partial positive charge. And this makes this proton easily leave. And because it can easily leave, it makes alkynes more acidic than alkenes, which in turn is more acidic than, sorry, alkenes, which in turn is more acidic than alkenes. So, for example, if we had a propane will be less acidic compared to a propene, which in turn will also be less acidic compared to a propine. Let's assume you have this terminal alkyne and you put in sodium amide. You are going to form this carbanion. And if you further add CH3Cl, what will happen is that, so let me show it here, CH3Cl. This carbanion will attack this carbon because the chlorine is a good leaving group, and it is going to give us CH3, C triple bond C, and then CH3. So this is the way plus HCl in solution. So if we create this carbanion, another thing we could have done is to put in a haloalkane like this. If we put in a haloalkane, this carbanion can pick this proton whilst causing this bromine to leave because it is a good leaving group. And therefore, in solution, we are going to form back our CH3, C triple bond CH, and then an alkene plus sodium bromide. So this is how this reaction will go. So this is how to produce both an alkene and alkyne in solution. You use a strong base like sodium amide or even KOH in ethanol. These are very strong bases. Then you can form this. You can extend the chain, or you can form both an alkyne and then an alkene in solution. If you have a vicinal dihalide on an alkene, you can convert it to an alkyne by first converting it to a haloalkene. So if you put in potassium hydroxide in ethanol, you convert it to a haloalkene, Cl, and then a proton here. Then you can further put in a strong base like sodium amide, and that will convert it to a corresponding alkyne. And also, if it was in this form, CH, so let's consider this example too. If you put in potassium hydroxide in ethanol, then one of these chlorines and an adjacent proton will go away to give us a haloalkene. So in this case, it's going to be CH3, C double bond C, then there will be a chlorine here and then a proton here. And there's another proton here. And then in the final step, if we put in sodium amide, then we are going to form this time a terminal alkyne. Instead of a dihalide, if we had a tetrahalide, you can convert it to a corresponding alkyne by using zinc in ether and then putting the solution through heat. If you do that, then you convert it to its corresponding alkyne. Let's talk about hydrogenation of alkynes. If you have an alkyne, you put 2 moles of hydrogen gas in a platinum, then you convert it to a corresponding alkene. But if you have a terminal alkyne and you put in hydrogen bromide in that solution, then what you are going to form is a corresponding haloalkene. If we put in another mole of the hydrogen bromide, then it will convert it to a geminal alkene. So, what is the mechanism that leads to the reaction above? Let's consider this alkyne. Assuming we have hydrogen bromide in solution, what will happen is that because this is a nucleophile, it will use one of its lone pairs of electrons to pick this proton, whilst causing this bromide ion to leave to give us. So this will be what will be formed in solution. Now, why there are two possibilities. It could also form like this. The proton could come here. So there is some form of regioselectivity in this reaction. This is also a possibility. But the reason why this will not form in solution is because in this case, the carbocation is on a secondary carbon. But in this case, the carbocation is a primary carbon. Carbocation on a secondary carbon is more stable than carbocation on a primary carbon. So let's continue with the one that will lead to the formation of the major product. So remember that there is bromide ion in solution. So it will attack this proton. And when it attacks the proton, it will lead us to this molecule. Now, if we add another mole of the HBr, then the lone pairs can come for this proton again, whilst causing this bromide ion to leave to give us CH3, C, then there is a bromine here. So in this case too, there are two possibilities. The proton could have gone to this carbon or to this carbon. But if the proton goes to this carbon, then that will lead to the formation of the major product, as in this case. And if the proton goes to this carbon, that will be a minor product. Now, why would the reaction favor this kind of product, this kind of intermediate? The reason is because the bromine can easily push one of its lone pairs to the carbocation, and that causes some form of resonance stabilization. So there is some form of resonance stabilization here. And it is this resonance stabilization that is the driving force behind this reaction. So in the final step, remember that we have CH, this intermediate. So the Br minus that was cleaved off will come and attack that center. Then we will form. So this is the final product that will be formed in reaction. And let's talk about hydration of alkynes. If you have an alkyne, you add H2O, you are going to form this product. And if you further put in another mole of water, then we are going to form a geminal diol. All of these reactions are regioselective. Another possibility is that in this case, there is what is called tautomerization. So this alkene alcohol can tautomerize to give a ketone. You have an acid here. So this double bond will use one of its lone pairs to attack this proton whilst pushing these electrons here. So in the next step, we are going to form this in solution. So it is, let me show you like this. So what then happens is that because we now have an H2O in solution, then water will use one of its lone pairs to pick this proton, whilst causing this bond to move into this place. And therefore, in the final step, we are going to form the ketone. But on an industrial scale, to form the ketone, what we do is that you use sulfuric acid in mercury sulfate, and that will cause the formation of the ketone in large quantity. And let's talk about oxidation of alkynes. If you have an alkyne and then you put potassium permanganate, then you are going to form a diketone to form in solution. If you put it in a more strict condition, that is heating the whole solution, then you form carboxylic acid. Sorry, there's a CH3 here. So this is how the oxidation of alkynes happens.